One of the reasons why we focused on the summation notation and sums just a moment ago is that we're going to be using them now to find the areas of figures. In Euclidean geometry, the simple type of plane region is a rectangle. And we often say that the formula for the area of a rectangle is the base times the height, when it's really actually more proper to say that that's the definition of the area of the rectangle. Based upon that definition of the area of the rectangle, the areas for the other figures can be derived, and those are the equations that we typically think of for the basic geometric shapes. If we go back to the ancient problem of trying to find the area of a circle, the way this was typically done was by the method of what's called exhaustion, which was due to Archimedes, I believe. The idea there, the concept was as follows. If I can take a bunch of, in this case, regular polygons, in particular triangles, and I can superimpose them by either inscribing them or superscribing them around the circle, that would give us an approximation for the area of that circle by adding the areas of the triangles, which is things that we do know how to do. And what will happen is, as we inscribe or circumscribe more and more triangles, the approximation gets better and better and better, so much so that if we take the limit as the number of triangles approaches infinity, the sum of that limit of those sums of those areas will approach the real true area in the limit of the area of the circle. For example, let's suppose we wanted to find the area under the curve negative x squared plus 5 between 0 and 2. If you look at the overall shape of this region, this isn't a basic geometric shape that you would have known from anything previously. It's not a nice polygon, it's not a circle, it's not a square. We don't have a formula for the area of such a shape. So we say, okay, this is what I want. What can I do? Kind of resorting back to that standard calculus trick and technique we've been discussing the entire semester. Well, the thing that we are very good at doing and the thing that we can do is we can calculate the areas of rectangles. If I were to go ahead and inscribe a bunch of rectangles into here, I would get 1, 2, 3, 4, 5 rectangles. I could calculate the area of each of these rectangles, the length of each rectangle, because we're using a set distance here. We're partitioning the x-axis into a set distance, which is of length 2/5. So the length of each rectangle is 2/5, and the width, if we want to figure out how tall each of these rectangles are, notice that each of these rectangles has a width that's determined by the endpoint of that rectangle, which is on the curve. So what we would need to do is stick the x value 2/5 into the function f to see how high it is, and that would give us the width of each rectangle. For example, rectangle 1, if I were to plug 2/5 into that formula, we would get negative of 2/5 squared plus 5, and that would give us the area of rectangle 1. I'm just going to do this off to the side. So if I were to plug, let's say, 2/5 in, or calculate that for 2/5, I would get about 242 over 125. Let's calculate the area of the second rectangle. It also is going to have a length of 2/5, and this is going to be negative the height of this thing would be found by plugging in 4/5 into the function. That'd be 4/5 squared plus 5. That would be 218 over 125. For the third rectangle, it would have a width equal to the value I would get if I plug 6/5 into the function. So it would be 2/5 times the negative of 6/5 squared plus 5. That's going to be 178 over 125. The fourth rectangle's width is given by the value of the function at 8/5. This is 2/5 negative 8/5 squared plus 5. That's 122 over 125. If I look at the area of the last triangle, its width is going to be given by substituting in 10/5, which is the same thing as 2. So I'm just going to call it negative 2 squared, or the opposite of 2 squared, plus 5 times 2/5. And that will work out to be 2/5. So this gives us the area of each of those inscribed rectangles. And so if I want an approximation for the area of the region that we're looking for, I can just go ahead and add up all of those areas. So the area of rectangle 1 plus rectangle 2 all the way up to rectangle 5, if we go ahead and do that, we would get an approximation of about 6.48. Furthermore, one of the things that we would know about this approximation is that the true area of this region is going to be a little bit more than 6.48. Because with inscribed rectangles, there's parts of the region's area that we're leaving out. So this would be an underestimate. But nonetheless, it's a fairly decent approximation, and it gives us some ballpark of what the true area might be, whereas we don't have a formula right now at the moment to find the exact area. We can do a different style of approximation by this time using circumscribed rectangles. And in this case, it's going to be the left endpoint of the function that will give us the area of each of these rectangles. So we have rectangle 1, 2, 3, 4, 5 again. To find the area of each rectangle, again, this is area equals length times width. The length for each of these is still that same standard fixed length of 2/5. And this time, if you look at the width of each rectangle, it's given by the height, which is the function value at the left endpoint of each region. So, for example, if I find the area of rectangle 1, this would be 2/5 times, I would plug 0 into the function, plus 5. This is one I can probably do in my head. This should be equal to 2. If we look at area 2, the area of rectangle 2, if I look at rectangle 2, it's right here. Its height is given by the left endpoint of its interval, which would be 2/5 squared plus 5. And that part was a calculation we just had done earlier. That's what, 242 over 125. It kind of matches up with this one from earlier. The area of rectangle 3 would have as its height, or width I should say, the function evaluated at the left endpoint, which is 4/5. So that's 2/5 times negative 4/5 squared plus 5. Okay, we have done that one already. That's 218 over 125. Just kind of skipping ahead a little bit, you can probably see what's going to happen here. But A4, the fourth rectangle, has as its endpoint 6/5. When we plugged 6/5 in, that gave us 178 over 125. And A5, the area of the fifth rectangle, has its left endpoint 8/5. When we plugged 8/5 in, we got 122 over 125. So if we wanted to approximate the area using superscribed rectangles, it would look like this. It would be 2 plus, so the area of rectangle 1 plus the area of rectangle 2, all the way down to the area of rectangle 5. And that would give us an area of about 8.08. So at least we have some kind of bounding, some kind of information for what we can expect in terms of the area of this region. What we're going to talk about now is how we can make that estimate better by using more and more rectangles, either circumscribed or inscribed, within the region.